Oh, yeah, that's great. Today we have 21st year, 21st century. Wait, 22nd. Oops, sorry. I apologize. I will check what is wrong after lecture because I've discovered that I have a problem with my stylus. When I write it dirty, I don't understand why. I've tried every possible way to discharge static electricity, but I don't know what's wrong. So I apologize for dirty writing because I have a lot of junk letters. I don't understand why it's so. My knowledge of physics probably is not so good. I don't understand what's the reason. Maybe I should change the stylus, but I don't know yet. Okay, so we have lecture 2. Today we will start optimization with inequalities. So the main topic is optimization with inequality constraints. Today we will cover this problem from intuitive and algorithmic point of view. So there will be no proofs today. So today we will approach intuitively and we will discuss step-by-step approach how we solve simple optimization problems with inequality constraint. So to do, we will focus on intuition and on let's receive a cookbook approach, yeah, cookbook procedure. So I will provide a rigorous proof later, not today. So don't expect everything will be rigorous today, but we will provide intuition, how to deal with inequality constraints, and we will provide cooking book procedure. So that's the plan for today. Let's start. Yeah. Any questions? Any ideas? If you know why the writing with the stylus on a pad screen can be dirty, just give me an advice. I will be grateful. Okay, just let's start with a very simple example. I have a so example 1 to build intuition. So let's consider a function f of x, just of one variable f of x, and a good function. So it's we have no problems with derivatives. So we develop intuition. So we do not care. It's a smooth function. We have no problem. F belongs to, let's say, continuous C1 class. No problem. Okay. So it's a smooth function. Derivative always exists. No problems with differentiation. Okay, what is the first order condition to find, let's say, maximum of f of x? What is the first order condition? You would like to find, let's say, local maximum. What is the necessary condition? Any question? Just to check if someone is present. Oh, yeah, I see. Yeah. Valerius, thank you. I have so the pad is, so I have tried this. Yeah, I have tried all these two ideas. Yes, I know them. That I have switched off. Yeah. I have tried everything. I have touched with stylus. I don't know how to say bateria. I have tried everything. I have switched off from charging. I have put a sheet of paper between my palm and the screen of pad. I don't know. Okay, so what are the necessary? But thank you for advices. Maybe I will try it once more. Okay, what are necessary conditions? What are first order conditions for extrema?
The first derivative is 0.
Yeah, at least one brave guy among 70 students. Yeah. Okay, first order condition is f prime is equal to 0. Okay. And now a more difficult question. What is the first order condition for minimization problem?
The same?
Yeah, the same. Yeah, you're right. That's okay. And now let's move to example 2. To build our intuition, now we have an inequality constraint problem. So we maximize some f of x, but we have inequality constraint. X is not less than 5. And let's draw 2 possible solutions. You roughly understand that either this equation, this constraint is binding, other it's really stops us for making better, bigger value of f of x. Either this is just irrelevant. Yeah, it depends on the function. Maybe we are limited. This is 5. So we are limited by our inequality constraint. Maybe the function is like that. So honestly speaking, this constraint, yeah, I don't care in this case. These are possible points of local maximum. And so f prime of x is, what is the first order condition for? Yeah, the same. Yeah. Don't be shy, please. That's all
equals to 0.
Yeah. But there is one interesting case. Yeah. There may be something like that. This is my possible values for x. I have a constraint. So that may happen that something like this, the function is growing. And in that case, local extrema are at point A, at point B, and at point C equal to 5. That is also a local extrema in that case, because I would, and this is A, B, and let's say C equal to 5. You see that on the right plot, I cannot obtain value of f higher than that in the point C. Okay, yeah, C is a point of maximum.
Yeah, sure.
Yeah, but if you look carefully at the derivative, yeah, it's a little bit different. We have 2 kinds of points. When x is less than 5, f prime of x should be 0. But if x is equal to 5, then f prime at x can be non-zero. In my point 5, my function is growing. Yeah? So f prime of x can be greater than or equal to 0. Okay, my function can be growing. Okay.
Yeah, okay.
So basically, we have, so first order condition in that case should change. Either f prime is 0 and x is less than 5, either x is equal to 5 and f prime of x is greater than 0. We can write this condition. So let's draw one more picture to show that we cannot have, so in our case, we can have 0 f prime, we can have positive f prime, but we cannot have negative f prime. So imagine how can that be if I have something like that. This is my 0.5. Yeah, this is the LO, and this is the region that for x that is possible. That is x. So I should write x here on the horizontal line. But basically, you can clearly see that that point is that point, the derivative is negative. It's not an extrema. Yeah, we can go left to the region of possible values of x, and we can increase f. So basically, there are two cases. So if we consider, so conclusion. So if we consider problem of maximization of f subject to inequality constraint, very simple inequality constraint, then we need to solve two cases. We have first order condition that is given by two cases, or that. X is less than 5. In this case, f prime of x should be 0, or x is equal to 5. In that case, f prime of x can be positive. Okay? Yeah, we have discovered first order condition for this simple problem. Any objections, any comments, any questions?
No, it's clear.
Okay, now let's write these conditions as one system. Then we have two cases, but let's write them in one system. So how can I make one system? So first of all, x is less or equal than 5. F prime of x is non-negative, but either I have two conditions. Either that should be equality. Okay, so I see that at least one of the conditions should be satisfied as equality. And so I add the third condition, x minus 5 times, or 5 minus x, I don't care for the moment, but let me write 5 minus x, multiplied by f of x is 0. Okay?
I'm sorry, can I ask one question?
Yes, obviously.
At 0.5, why the derivative cannot be less than 0 if, for example, graph starts to diminish?
That is the case. In the derivative at 5 can be negative, but in that case, this is not a maximum. I'm searching first order condition for maximum.
Yeah, I mean, and if a 0.5 is is some sort of boundary,
Yeah, like that.
on the left side, the graph increases, and like on the right side, the graph starts to decrease. Ну, то есть, если это что-то по типу пика, только как бы не такого пика, в котором природа не существует, а да, вот что-то типа такого.
In that case, f prime at
0.
5 is exactly 0.
Да, все, спасибо.
And this case is allowed. Equality is possible. So equality is possible. Yeah, you're right. That's possible. Yeah, we may have. Okay, so we have written one system that takes care of both cases. Yeah. Now let's discuss the case and discover a strange property that when we consider equality constraints, first order condition for minimum and for maximum are exactly the same. You just write Lagrangian function, take derivatives, they're equal to 0, bingo. And you can find minima and maxima. So you don't care whether you are searching for maximization, for minimization. In our case, yeah.
Excuse me. Should we change sign of inequality in the case of f prime of x if we use minimum?
Yeah, exactly. Let's solve the let's discover first order condition for maximization. So let's look. So if we try to minimize f of x, and we have exactly the same condition, x is less or equal to 5. So our region that is allowed is to the left of 5. Yeah. There may be, once again, two cases. The first case is something like, that's something like that. This is local minimum. Yeah. And in that case, x is strictly less than 5, and f prime of x is 0. It's case A. And we have case B. What is case B? We have 5 there. The function is roughly like that. And we would like to go to the right of the point 5, but that is not possible by our constraint. And so in this case, x is equal to 5, and f prime of x should be, should have which sign?
Less or equal.
Yeah, less or equal to 0. And finally, we may combine these two cases in one system. Which one? What are the possible values of x? Can be x greater than 5?
No.
No, x is less than 5. Can the derivative be positive?
No.
No, so f prime of x is less than 0. And finally, we cannot have x strictly less than 5 and simultaneously negative f prime. One constraint should be satisfied as equality. Okay? One equality, we should have either f prime is 0, either x is 5. So we need which equation? We need to add one equation.
Exactly the same as the previous.
5 minus x times f prime of x is equal to 0. And this system will take care of both cases. Okay? Yeah. So we have, even after considering this simple case, we can write some concluding remarks. Yeah. So we can, we have made some discoveries. What do we have? What are our conclusions? Basically, we have first order condition for minimization problem. So first important condition, that's very sharp difference between inequality constraint and the case of equality constraint. So first order condition for minimum are not the same as first order condition for maximum. So when you are asked on the exam to solve to find all extrema, not just all maximum values or minimal values, when you are asked to find all extrema, so first you check first order condition for minimum, you check second order condition for minimum, and then you check first order condition for maximum, second order condition for maximum. Okay, so it's a little bit long. Yeah, inequality problems they take much more time. So you cannot just economize it. So, oh, I will solve I will solve a system, and there will be points of maximum and minimum, and I need only to classify them. No, that approach does not work. So, second conclusion, that solving extremum problems with so it's conclusion of the first with inequality constraint, inequality constraints takes much more time. That's a bad conclusion. Yeah, takes much more time. Roughly twice as much time. The first difficulty is that you need to repeat almost the same system of first order conditions with one inequality inverse reversed, sorry. And second, you have a system. This system is a little bit harder to solve because you have equalities and inequalities, not just equalities. So the third conclusion, it's better to avoid solving the system. So avoid solving systems with inequality constraints. You may ask me, how can I avoid? I'm arriving at exam and there is a problem with inequality constraints. How can I avoid it? And advice sometimes it's clear from the statement of the problem that so avoid solving systems with inequality constraint if possible. Yeah, maybe it's better to add that sometimes it's possible to ignore inequality. So I will provide you example what I mean. So for example, you are required to maximize given, I don't know, x greater than 0, y greater than 0, z greater than 0, x to the power, I don't know, 5, y to the power 7, z to the power 6, subject to 2x plus 3y plus 4z less than or equal to 100. And it's much more reasonable not to delve into these problems with methods we will discuss, but to just say, but it's obviously, if I'm maximizing the product, x, y, z, then I'm sure that at the optimal point, 2x plus 3y plus 4z will be exactly equal to 100. Yeah, because if it's not equal to 100 in the optimal point, then I will increase x, and I will have a bigger product. Yeah, so in optimal point, 2x plus 3y plus 4z is exactly equal to 100, and this will greatly simplify all calculation. So this is very important advice. When it's possible, when it's when you can see from the statement of the problem that inequality is satisfied at the optimum point, then just replace inequality constraint by equality constraint if that's possible. You will save a lot of time. You will reduce greatly the probability of arithmetic errors. So that, believe me, many students ignore this possibility to say, yeah, we need to make the product bigger, so we need bigger value of x. If at optimal point 2x plus 3y plus 4z is strictly less than 100, then we have opportunity to increase x, and that's not optimal point. In optimal point, we don't have opportunity to increase the value of x without reducing the value of y and z.
I'm
Okay?
sorry, and
Yeah.
Can I ask one more question about
Yes.
your previous example? It's stupid a bit, but still. Why do we care about the derivative at the boundary point? In that case, it was a point of a value of 5.
Yeah.
If we can just always calculate the value of a function at this point and just compare that value with values found with the help of derivatives.
Yeah, in that case, you are completely right. In that case, when you have only one point, then it's not a problem. But when we solve problems with many variables, then boundary, it's not one point. You may have, in this example, you are completely right. It's better to just calculate the points where the derivative is 0, calculate the point at the boundary. You may have one point when you work on the line, and you are happy. You just compare the value. Yeah, bingo, you won. The problem is in multivariate problems, because in multivariate problems, you have such a, so for one variable problem, you're completely right. That's the way you solve it in school. Yeah, but when you have a boundary like that, you have infinite number of points on the boundary. Yeah, so we need a method to work with infinite number of points. So we need a system of equations or inequalities.
Okay, thank you.
And stop wasting time. Just don't ask whether I can ask question about, whether I can ask question. Just ask the question. If we have time, I will answer it. If we don't have time, I will say, sorry, write me after the lecture. I will explain, but sorry, we are short of time. But so just don't ask me, where can I ask the question? Yes, you can, always. Okay, let's move on. Let's move on. So let's now work with a two variable case. Yeah, let's do the same thing in two variables. Now we have two variables case. Two variables case. Imagine that we have a problem of maximization of some function f of x and y. And now we have an inequality constraint. Let's say j of x and y is less than, I like 5. You may put b there, but the logic will be the same. I will less than 5. So once again, I may consider two cases. First, I will consider two cases, and then I will combine them into one system of equations on inequality. So the logic, I will consider two cases. Case one, when we maximize f of x, y, and our g is strictly less than 5. And case B, we maximize f of x, y, but our j of x and y is exactly 5. So how we do proceed in these cases? Because in the first case, case A, let me draw the picture. So imagine that our constraint G is something simple. Yeah, they may be very complex arbitrary regions on the plane, but I will understand the intuition with simple form of these possible region for X and Y. So let's imagine that it's something like, to simplify, so we will think of it like J of X, Y, like imagine that it's like X plus Y or something else, simple. Okay, so we have an available region. In the case A, we cannot be on the boundary. So we cannot stay on this line. We should be below this line, inside a region, not on the boundary. And in that case, once again, derivatives should be 0. So in this case A, first order condition will be f prime with respect. So now I have two derivatives. F prime is 0. F prime with respect to y is 0. And my g of x, y is strictly less than 5. So that is first order condition for the case A. Let's consider the case B. You know how to solve this problem. How can we solve the problem of maximization given some equality constraint?
So we can use the method of Lagrange.
Yeah, exactly. If you have some, let me draw something. Let me draw something to do this. In blue, I will draw level curves, so they do not intersect. They just, that's a bad idea to have intersecting. So that will be the level curves. So that will be level curves of F. Okay, let me show you case B.
I'm sorry, and so these curves mean that you could just fix some variable and then have considered value of another variable, right?
Sorry, this is the set so where f is constant. So imagine that f is then f is
for example, x times y equals 5, right?
I should have two hills. So we have two hills. I have two hills. So,
No, okay, but not precisely for this graph, but in general. Okay, I think I've got the idea.
Okay, let's continue. Okay, let's go with case B. With case B, I should be on that line. The second, my constraint is transformed into equation. I have x there and y there. And I will draw once again level curves. So let's imagine that is then like I will draw small lines. These small lines, like on the maps for orienteering, I will show you with such small lines. That means where the sticks will, so it means that, so when I draw a level curve and add a small line, that means this line has equation f equal to, I don't know, 42. On that side with a small tick, f is less than 42, and on the side without tick, f is greater than 42, just to understand using level curves where does the f grow. Okay, so the f is growing. Oops, I have two hills, one hill and another hill around. Yeah. Any questions for the moment? Okay, I think no question, but be active. Just say, oh, that's fine. Let's go. Boom, boom, boom.
That's okay, it's clear.
Thank you. And the problem with dirty steel has disappeared. I don't know why. It appears and it disappears. I don't know. Okay, so let's think. If I'm on that line, the best point. Yeah, I will draw a third. I will draw a third hill. Yeah, I will draw a third hill. A third hill will be there. I will draw a third hill, but my third hill will be on other side. So, and how can I write it? So I will just show you the height of my f when I move on along the line. So when I start here, the value of f is small. When I move to the right, my function f grows. So it roughly, when I arrive somewhere here, the function is maximal. Then I continue, my function drops, my function decreases. Then again, I enter the third hill, the middle hill. So my function is like that. Yeah. And when I continue, once again, I enter the third hill and it goes down. Okay. So this is a profile of my function when I move on along my line. Okay. Any questions? The picture is clear?
Yes, it's okay.
Okay. Now, let's say that at first it seems so the two-dimensional picture is a little bit difficult. Okay, when this point is so I have 3 points, and let's think which of them are suspicious to be local extrema, A, B, or C. If I'm at the point A, or when I'm required to be on the line, then yes, it's local extrema. But if I go back to my original problem, I can be either on the line or I can move below the line. So if I'm at this point, in this point we have, in this point my line is tangent to the level curve, but I can increase my function. I can go up the hill. Yeah, I can increase the height. So that is not a local maximum. Okay, if I consider the point B, the point B is somewhere, so I will copy coordinates. Let's use red color. This is A, this is B, this is C. If I'm at the point B, can I increase locally my height or not, without violating my condition that g of x and y should be less or equal to 5?
No.
No, because to go up to the hill B, I need to break the rules. I need to go into to move up the hill B, I need to have j of x and y greater than 5. So B is a local extremum, local maximum. And what about C? If I'm at the point C, can I increase the value of F without breaking inequality constraint?
Yes.
Yes. Okay. So this is not a local maximum because I can go there to be higher on the hill. Okay, so now we have understood the geometry, and let us write this in in a system of equations. Okay. So what do we see? Let's write first order condition, first order conditions for the case B. Yeah. We introduce Lagrangian function, that is f plus lambda, lambda, let me say 5 minus j. And I will have f prime with respect to x minus lambda g prime with respect to x should be equal to 0. Okay. What do I have next? I have f prime with respect to y minus lambda j with respect to y equals to 0. Okay. And I have j of x, y is equal to 5. Yeah. Everything is okay?
Yes.
Okay. Let's combine everything in one system. That will be a little bit more difficult, but let's develop our intuition. Okay. We'll combine everything in one system, and we will discover so I will write something like first I will notice that these two equations will be the same if lambda is 0. If lambda is 0, then this is the same equation. Okay.
Yeah, okay.
Okay, so I will say that f prime x minus lambda x prime is equal to 0. F prime y minus lambda j prime y is equal to 0. J of x y is greater than equal to 5. And what may happen? If lambda is 0, then so I may have either, this is the case, lambda equal to 0, and this is the case where j of x y equals to 5. So I have two cases, and to combine them in one case, I will write lambda times j of times 5 minus j of x y equals to 0. Why so? This is roughly like, if you remember the case of one variable, this is like in one variable case, that was something like f prime of x times 5 minus x was 0. Do you remember that additional combining constraint?
Yes, you do.
Yeah.
Okay, and now we have one more more constraint. So this is necessary. This is first order condition, but one condition is necessary. So we have one missing condition. If we will write it, then we will completely discover everything. So the last condition is missing. I will try explain the last condition now. But roughly, we see that we have combined in one system. We have combined points where g is strictly greater or strictly less than 5, and we have combined points where g is exactly 5. So let's discover the last condition. The last condition is about we need to exclude. This is okay, but there are too much points that satisfy our combined first order condition. That's almost okay. The problem is that, so let's imagine some points like this will be the point A, B, C, D, and that will the point E. Okay, so let's check whether our combined condition will trap all the points. Why D will be trapped in our condition? D will be trapped because lambda equal to 0 is allowed. So D will be trapped. Okay, D is trapped. Okay, yeah. Why E is trapped? Why E is trapped? E is trapped because lambda equal to 0 is allowed. So we just put lambda equal to 0 and everything is fine. The problem B is why B we have why we have B point, because B is trapped. B is trapped because in the point B, g of x and y is exactly 5. So this condition is satisfied as equality, and these two okay. The problem with our combined first order condition that we have bad news. There are also 2 points A and C that should be excluded. They are not optimal. They are not maximal points, but we have trapped them. Yeah, we need to this conclusion with this condition. We need to exclude A and C because they are not a local extrema. Okay. Any questions up to the moment? Because we are just building intuition. We are not discovering some.
Excuse me, and can you explain one more time why D and E is trapped if lambda equals 0? I didn't get it a little bit.
The first order condition for the points D and E is the following. If we are searching for internal points, not on the boundary, but internal points, if we are searching for internal points, like in one variable case, you make f prime equal to 0, f prime to y with respect to y equals 0, and we are searching for internal points where g is strictly less than 5. So this is a system to find E and D. Solving this system of equations, you will find point D and point E, because both derivatives are 0 at point D and E. Okay, and if you look at our combined system, our combined big system, if you start
now I see
it, you will either, so you may start from this equality. Either you will have lambda to 0 equal, either you will have g of x, y equal to 5, and that will give you the first case, and that will the second case B, and lambda equal to 0 will give you the case A. Okay.
Yeah, thank you.
Okay. The problem with our combined system that we have 2 junk points. We have 2 points that are not optimal. They are not maximal points. They are they are on the line, but and the quest is a little bit. So we have a subtle idea to remove bad points that are not extrema. So our system is okay. We have too many points. So we have done, let's say, one half of a problem. We have obtained a system that will catch all the suspicious points. But our system, our combined system, will catch too many points. So I don't need so many points in first order condition. Okay, let's remove these two intruders. So let's remove these two intruders. We need to deal with. So let's interpret this condition geometrically, and using geometric interpretation of these two conditions, we'll remove intruders A and C. Okay, so what is the geometry behind first two equations? So f prime with respect to x, f prime with respect to y. This is lambda times g prime with respect to x times g prime with respect to y. I have just rewrite it so this was the beginning of my combined system, f prime minus lambda g prime equals to 0, f prime with respect to y minus lambda g prime with respect to y. So that was the beginning of my combined system, and I can interpret this beginning geometrically. So that means gradient of f is proportional lambda to the gradient of my function g. Okay. Yeah. That's fine.
Yes.
And let us look at our so I will just to make okay. So let me look at something like let me draw once again my situation. This is the region G of x, y is less than 5. And I have a hill that is with the top of the hill is there. Another hill that is there. And one more hill that is in the possible side. So this is a point A, this is a point B, this is a point C. Point A is not an extrema because I can climb the hill A. B is maybe probable extrema because maybe the hill B is very steep, and even the first step in the direction of the hill B gives me plus 1 million in the function. Maybe the extrema is here. And point C is not an extrema, once again, because we can move inside our possible region, and we can increase the value of the function g. Okay. Now, let me draw the gradient of f, and let me draw the gradient of g. Okay. Let me draw the gradient of f and the gradient of g. This is in blue will be gradient of f. In this point, the gradient, if you remember, the gradient is orthogonal to the level curve, and it shows you the direction in which the function will grow. So the gradient of f here shows me the direction in which I see the top of the hill. The gradient in the point B shows me that direction. The gradient in the point C shows me that direction. Okay, we have drawn gradients of function f in various points. Any questions up to now?
No, no questions.
Now, let me draw the gradient of G. I know that on that line, G is exactly 5. So G is less than 5 to the left of the line, and G is greater than 5 to the right of the line. Once again, gradient shows you the direction in which the function grows. So in this case, the gradient is there, gradient is there. In that case, gradient is there. And I see that in this case, my lambda is, oh, sorry, just a moment. I will check. I have a maximization problem. 5 minus j is 2. Just a moment. I should have that lambda is positive, and I have that lambda is negative. It's unexpected. I know the answer, and it happens that the sign is switched, and I'm searching whether I have switched the sign. So f, I have a maximization problem plus lambda times 5 minus my function j. That's everything is fine. So 5 minus j. That's strange. That is. Yeah. Everything is fine. Sorry, everything is fine. And I see that lambda should be the ratio of, everything is fine. Sorry, everything is fine. Everything is fine because point A, I should exclude it. Point B, I should include it. And point C, I should exclude it. So from this picture, I see that in good point, lambda, in that case, I see that lambda A is negative, lambda B is positive, lambda C is negative. Yeah, gradient of f should be proportional to the gradient of G, and to exclude points A and C, we should impose that condition. Okay? Any questions? Because we have discovered our necessary conditions. We will just write the final answer and.
So then we state that lambda should always be more than 0, right?
More or equal to 0 to case.
Or equal,
so
yeah.
for case on the line. So for case on the line, maybe the top of the hill exactly on the line. So we should have, so equality is possible. Maybe the top of the hill is already on the line. And so our final answer for two variables case is the following. We need to maximize f of x and y subject to g of x and y less than 5. And we introduce, so the logic, we introduce Lagrangian function f of x and y plus lambda times 5 minus j of x, y. We write L prime of x, that will be f prime of x minus lambda g prime of x, and should be 0. L prime with respect to y, f prime y minus lambda g prime y should be 0. What else? Isa lambda isa 5 minus g prime g of x and y should be 0. 5 minus j of x y should be greater than 0, and lambda should be greater than 0. And basically, we have discovered first order conditions for that problem. Any questions? Because that's an important point. We have discovered, and then we may move on to the, because the general case when you will have a lot of.
Could you please explain once again about the picture gradient of g function?
Yeah. What we know about gradient? We know about gradients two ideas. First idea, gradient is orthogonal to the level curve, okay?
Yeah.
Second idea, gradient, there are two orthogonal, so if you are orthogonal to a line, you may go in two directions, yeah? So the first idea, the gradient is orthogonal to the line, but you have two half planes. Yeah, you may be orthogonal in that half plane, you may orthogonal in that half plane, okay? And if you need to choose which in which half plane the gradient is, then you just need to understand the idea that gradient shows the direction in which the function has the highest growth rate. Yeah.
Yeah.
Second, geometric interpretation of gradient. Gradient shows me the direction in which the rate of growth of the function is the highest. Okay, let's once again, we using these two ideas, we draw the gradient of f. These curly lines are level curves of f. So my blue gradient should be orthogonal to the blue line, and it should point in the direction in which the function f grows. So I draw blue gradients. Blue gradients are orthogonal to the blue level curves, and blue gradients, they point in the direction of the of each hill. So here the function grows locally to the top of the hill A, then to the top of the hill B, and then to the top of the hill C, okay? So we have drawn blue level curves.
Yeah,
and now we move on to the black level curve. Black level curve is that line, because this line, it's a straight line. To simplify our exposition, we have imagined, we have drawn only one case, but to build up the intuition. So our level curve is just a line. No hills, no complex trajectories, just our level curve. So this is level curve. Level curve. It's a level curve, but it's just a straight line. So my black gradient should be orthogonal to that black line. And then I need to find the direction in which my function g will grow. This is a line. This is a line when g is equal to 5. That region is forbidden region. I cannot go there. There, g is greater than 5. This is allowed possible region when G is less than 5. And so in which direction should point black gradient? It should be orthogonal to the line and pointing in the direction in which the function grows. Okay, so all black gradients go in the upper right side, or in the upper right direction.
Okay, thank you. I got it.
Okay, and I see that in a good point B, in a suspicious point B, blue gradient and black gradient, they are just proportional with positive coefficient. And in bad point, I should exclude them. They are not candidates for extrema. In point A and in point C, blue gradient and black gradient, they lie on the same line, but in opposite directions. And I should exclude that case. So lambda should be non-negative. Okay.
Yes, clear.
And the general case. So if you have understood this, then the general case, the general procedure, the general first order condition will be, imagine that you have a maximization problem. We will write, so you have a lot of variables, x1, x2, xn. So the general first order condition will be like this. And you have some conditions like g of x1, x2, xn is greater than, let me write greater than 0. Yeah, let write greater than 0. Will be g1. g2, x1, xn is greater than 0. And let's say gk, x1, xn is greater than 0. Okay? And we have, or maybe we have even old constraints. Let me introduce some old constraints, like h of x1, xn is 0, some old type constraints. Yeah, h of x1, xn is 0, and h kn, what I have not used, p of x1, xn is 0. Yeah, what will be the first order conditions? Yeah, let's write the general case. If you have equations like less than 0, you can always make them greater than 0. So if you have some equation x squared plus y squared is less or equals than 10, you can just go into that form like 10 minus x squared minus y squared is greater than 0. So it's not really it's a convention. Yeah, I will say that I'm maximizing a function given that constraint. Okay. I have two types of constraints, either equality constraint, old type, old year, yeah, and new type, inequality constraints. And then how can I do? We will discuss in DCQ later because it's a little subtle. Okay, so we omit in DCQ discussion for the moment. But if we speak about first order condition, and we do not discuss second order condition yet, yeah, but the procedure is like with before, is like before New Year. So we have in DCQ first order condition, second order condition. Now let's discuss the first order condition in general. So we build a Lagrangian function in which we include our f of x. Yeah, let me write x as x1, xn. It will be a vector. We know linear algebra, so that should be not a problem. Okay, plus we have sum from I ranging from I to k. We have lambda I times gi of x, plus we have all the type constraints. sum from equal to 1 to equal to p. Let's call all the constraints, let's call them Lagrange multipliers. Let's call them mu multiplied by h of x. We construct a big Lagrangian function, okay? And now, what are the first order conditions? Let's write them all. First order conditions. Yoo-hoo! L prime with respect to x1 should be equal to who is with me?
0.
0. L prime with respect to x2 is 0. And so on. L prime with respect to xn is 0. Okay, let's these conditions should be satisfied also. So original constraints, original. So every g prime, every g of x is greater than 0. Every h of x is exactly 0. This is a copy of constraints. Now, we have discovered then we work with inequality constraints. Lambda should be non-negative. So lambda 1, lambda 2, lambda k are non-negative. There are no conditions for mu because mu are factors before all the type constraints. And finally, if you look carefully at, so what do we have? This is mentioned, that is mentioned, that is mentioned, that is mentioned. So we need, what is this? This is lambda times constraint should be 0. So in our general case, g1 of x times lambda 1 should be 0. Gk of x times lambda k should be 0. And finally, bingo, we have finished. Yeah, and the time is exactly 40 minutes. Perfect timing. Yeah, first order constraint. And we have developed intuition. We haven't proven them strictly, but we have provided intuition. Why do we need these strange condition? Why we should multiply? Because this multiplication basically is idea. So what are the ideas behind these system? This is the idea of combining two cases. And that one is the idea that we should exclude points on the boundary for which we can switch from the boundary inside allowed possible region and have a bigger value of function. So these conditions for non-negative lambdas, they prohibit situations in which I'm on the boundary and in which I can move from the boundary and increase my function. Okay. I don't know. Okay, so
Excuse me, and what is written on the fourth line before any g?
Original constraints. So these are just copy of original constraints.
Thank you.
So if you look at original constraints, every h is 0, every g is greater than 0. So that's just a copy of original constraints. Every h is 0, every g is 0 or bigger than 0. Okay?
Yeah, thank you.
Excuse me, and H is a different set of constraints, right?
You may have a combination of equality and inequality constraints. So we may solve, I don't know, maximization of x squared plus y squared plus z squared subject to, I don't know, x plus 3y plus 4z is less than 5, and x plus 2z minus y squared is exactly equal to 16. So this is inequality type constraint G. This is equality type constraint H. Okay.
Yeah, okay, thank you.
So you have basically two types of constraint: old type constraint, equality constraint, and new type constraint, inequality constraint. So today we have built intuition. We have not proven this rigorously. So next time what we plan to do, we will solve some examples, and then we will, so I think we will continue with examples, so to better understand, to get used to these conditions. So we will work with NDCQ, we will work with second order condition, and then when we have experience, we will provide a honest proof of these conditions, because that we have created them from two examples, from one variable example, from two variables example, but the idea is to not to just only to, we are doing math finally, and the idea is to have some proof. Okay. So see you next time.
Sorry. Where will you upload this recording?
Yeah, I will upload. Yeah.
Where?
There will be, for sure, you will have a link from information system. Yeah, that's a good place to
Thank
start.
you.
Okay, just wait a little bit. I will. Yes.
Can I ask you for a second to show the two variables case? The first
Sorry?
order condition for that. Can I ask you for a second to show the first order condition for two variable case?
Two variable case. Yeah. Two variable case. Yeah.
Yeah, thank you.
Okay. So have a nice.
I don't have questions. I just want the answers. Until
Okay.
Thank you.
Bye bye.
Thank you. Bye.